Hello everyone, I welcome you on today's session about memory management in the subject Introduction to Operating System. So we'll see about what is memory management and basic technologies inside the memory management. So before getting into the topic, let me introduce myself. I am Shanmuga Priya, working as an assistant professor from Computer Science and Engineering in Mahendra College of Engineering, Salem. So before getting into the topic, we'll see what is memory management. So memory management, we know this memory management actually exists in operating system. So what is an operating system? There has been so many definitions. If you take a simple definition, this operating system acting as an interface between the user and the system. The operating system acting as an interface between the user and the system. So if you take this operating system, it is nothing but a set of programs. The operating system is nothing but a set of programs which tries to carry out the output required by the user through the input whatever we given with the help of the specific hardware and software present inside the system. So that is what operating system. It simply acts as an interface, or it coordinates what are the various devices present in the system and helps us to acquire the desired output. So that is what an operating system is. So if you take the functions of operating system, there has been so many functionalities of operating system. There has been so many functionalities of operating system. It is of an example, it is a process management. It helps to manage the memory, it helps to manage the storage, it helps to manage the files present in the computers. So these things helps us to present or manage what are the units or the device present inside the system. So it's mainly helps us to coordinate what are all the modules and the devices present in the system. So system is nothing but, we all know, a system comprises of CPU, input unit, output unit, memory unit, storage unit, etc. So control unit, like that there has been so many units present in the system. So this operating system helps to coordinate or access all the units together and helps to provide or helps to create the desired output for the user. So that is what called operating system. So there has been so many functionalities of operating system. One of the main functionalities of operating system is to manage memory. So this memory management helps to acquire system performance improvement. So you can manage this memory in such a way so that you can improve the system performance, and through this memory management we can manage the process as well. And also through this memory management technique we can handle the shared memory, and there has been various techniques to manage this memory. If you take for example, there has been paging, segmentation, so many concepts are there. Even we have this virtual memory concept. There has been so many concepts in managing the memory, and also it is also dependent on hardware and the software presence inside the system. So this hardware and software inside the system contributes the main value to this memory management technique. So what are we going into see in this memory management topics are logical. What is logical address space? What is physical address space? How we can protect this address space, and what is binding, and what is contiguous memory allocation? All these things we are going to see in this lecture series. So first before getting into the topic, we'll see how this memory actually works. So inside the operating system, you can take an example. Whenever you try to access any file present in the system, whether it is a laptop or it is a desktop, whatever it is, any file is present in your computer, laptop or desktop, it is always in your hard disk. So that is nothing but your disk space. All the files what we were trying to say is present in the disk space. So whenever we try to access the file, what happens? That file will be brought back to the CPU, and then brought back to the CPU memory, and then it will be displayed from there, from the memory. So this memory, if you take in operating system, there has been so many types of memories. What we know is a disk memory, which is nothing but a secondary memory, and apart from that there has been so many types of memories available. For example, we can say primary memory, secondary memory. So into that primary memory we have so many subtypes. Like from primary memory we have RAM, ROM, registers, cache memory. So these are very important memory. These memories only helps us to yield a better performance compared to the disk memory. So even we require a lot of disk memory, but compared to the secondary memory, primary memory is very much efficient for during the running process by the operating system. So whatever is there in the disk memory or the secondary memory, that will be brought up to the primary memory and during execution time, and from there it started executing from the primary memory, and the result will be stored into the secondary memory. So this is what usually happens. So that is what has been shown here. So whenever you try to run any program, that will be present in your disk, which is nothing but your secondary memory, and that will be brought back to your primary memory, and it will be executed from the primary memory through RAM, cache, registers, etc. So if you take primary memory is very important memory. So to manage these concepts, we need to understand what is a physical address, what is a logical address, etc. So whenever you access any request, whether it is a read request or write request, which is nothing but you're trying to open a file or you're trying to create a file or trying to delete a file, we need to know what is happening at the back end. So this operating system is capable of moving a file from the secondary memory to the main memory, and it helps to generate the physical address and virtual address and then logical address, etc. So the main two addresses nothing but physical address and logical address. We will see what is this physical address and logical address. So that is nothing but logical address. So logical address is generated by the CPU, which is during the runtime, which is also be referred to as virtual address. So whenever you try to access any file, there they generate, this operating system generates the logical address, which is we call as virtual address, and then it will display the memory contents to the user from the logical address by fetching it from the physical address, which is nothing but your secondary memory, by fetching it from the physical address, which is nothing but your secondary memory. So this logical address is nothing but generated by the CPU, and physical address is nothing but what are the memory address we see in the disk space, we refer it to as physical address. So as you can see here, there has been more than one process used to execute at a time. So that obviously improve the efficiency of the program or the process or the operating system. To achieve this, we have to ensure whether all the processes accessing the memory properly by providing a proper logical and physical address and address binding mechanism with the help of the operating system. And in turn, we have to protect the operating system and the memory space shared by these processes. So how we can do, we'll see. Here I have shown one example. There has been operating system, there has been number of processes are available in the operating system. We have limit register and base register. This limit register is nothing but the starting address of your process, and then this base address is nothing but your the base limit of the process. So here you can see the limit is nothing but the starting addresses from 0 to n number of bytes, and you can see this operating system, the process 1, process 2, there has been n number of processes used to execute. So for each process we have this base address and the limit address. Base address is nothing but the starting address of your process, and the limit address is nothing but the maximum range of your address. So within this base address and the limit address, the process values or process data will be available. So whenever there is an execution, we have to provide the base and the limit address so that the CPU or the operating system navigate within those limit, and then it will try to execute the data. So with the help of this hardware, we can able to create a base and the limit registers with a limit register address, and then you can navigate the data available within the base and the limit register address, and you can read the contents or write the data into the memory with the help of this base or limit registers. And another thing, as I told you, this base registers and limit registers will work with the help of the concept of logical and physical address. So this logical address and physical address we can be bind with the help of address binding mechanism. So which is this address binding mechanism try to locate the physical address value into the some logical address value. So that is what called binding. So in binding you can see there can be a source code. So from the source code, whenever the source code is run by the program or we run the program with the help of a compiler, then the compiler will break down the program's parts into modules and then symbols and the segments, tokens, etc. And also after breaking down into small units, then we'll do the linker, we'll do the linking process. After finding the linking function, the particular linking function will be loaded into the compiler and then it will be executed into the memory, and then the result will be stored back into the physical address. So this is what usually happens whenever we run a program. So binding of instructions, whenever you try to execute any instruction, it can be an add instruction or it can be a multiply instruction, we have to load the corresponding data into the memory. We have to load the corresponding data into the memory. This is called the binding of instruction and data to the memory. So that happens in a set of process. For example, let us say first the compile time, load time and execution time. All these things helps to regenerate the result or generate the result that has been that going to be executed first or regenerate the previous executed results. So we have seen what is the logical and the physical address. As I said, this logical and the physical address is nothing but which helps us to execute the program in an efficient way so that the process will protect the data in a particular memory. So who will be maintaining all this, generating a logical address and mapping that to the physical address is taken care by the memory management unit. This memory management unit is also capable of securing the memory from one process to another processor. Even though we might be sharing the memory, this memory management unit is capable of managing and maintaining the securing the address space from one process to another process with the help of this relocation register. So relocation register is nothing but we add some generated address that to the actual existing address, physical address, and we create a logical address. Through that logical address we execute the data, and if it is a necessity that we will store back into the physical address. So that will be taken care by this memory management unit. That will be taken care by this memory management unit. So you can see here this relocation register process, working process is nothing but from the CPU we generate a logical address. Through this logical address we will generate a relocation register. So this relocation register is nothing but it generate some temporary address. With the help of this temporary address, what we'll do, we'll generate the physical address. This generation of physical address is already existing in the disk space. So from the figure it may look like it is generating, but is not actually generating. From the physical address only we navigate, we add some value with the help of the base and the limit register, and we generate a temporary or logical address or virtual address, we can say. These details all will be located into your relocatable code or relocation register. So whenever there is a necessity look of physical address and logical address and their relationship, then that operating system is looking into this relocation code register and then retrieve the data from this register, and then it will be displaying it to the user. So when there is multiple process residing, then there is a possibility of how we are going to access and store the data. So we can store and access the data through contiguous and non-contiguous memory allocation technique, or fixed or variable partition techniques are available. All these techniques helps to access the memory available in the memory unit. So if you take this memory unit helps us to divide the existing memory space into different partitions or different holes or chunks or pages or different sizes that is required by the instruction to execute. So that is what this memory, this management technique, one of the main concept. So if you take this contiguous memory allocation, you can see here it starts from the 0 and to the end. In a continuous way, it will allocate the process whatever it is coming for execution from the ready queue, and it will allocate the process memory address in a contiguous memory allocation method. So in contiguous memory allocation, we can simply refer the allocation is basically in terms of two partitions, which is nothing but the resident operating system, which is nothing but the low level of memory, and the user process, which is present in the high level of memory. So each process, whenever it is running, it requires contiguous or non-contiguous memory allocation for running its process. Whenever there is a process, as I told, there has been n number of process will be ready for executing. So while executing n number of process, for each process to execute, we require a memory space. For that memory space can be a contiguous way present in the memory or non-contiguous way. So if you take this contiguous allocation, if you take this single partition or fixed site partition. So fixed site partition, as I told, the memory whatever is available will be divided into fixed sizes. So when you take this fixed size of partition, each partition will have fixed sizes of memory. So these fixed sizes of memory will be given for the execution of the process. Actually, these fixed size partition leads to internal fragmentation. So internal fragmentation is nothing but whatever the memory available, I'm divided into equal blocks and giving for execution. If the required process requires very less amount of memory, but I am giving more amount of memory block for the process to execute, then it leads to internal fragmentation, which is nothing but the required process getting more number of memory size than the actual execution size, then it leads to internal fragmentation. So an example for this, contiguous memory allocation has been implemented in IBM OS 360, and then we have this variable partition scheme. So in order to not suffer from this internal partition or internal fragmentation, then we go for this variable partition scheme. So in that, each process will be given different sizes of memory. So each process will be given different sizes of memory. So we can call it as a dynamic memory allocation. So whatever the different sizes is what we call it as whole, which is nothing but a block of memory. The block of memory is nothing of various sizes scattered in a whole memory. So whenever you try to allocate these various blocks or sizes of memory available, then there is a possibility of dynamic storage allocation problem can be solved using first fit, best fit and worst fit techniques. First fit is nothing but whenever a process comes for execution, whatever the process available from those whatever the memory is available, from those memory we'll choose one whole, which is nothing but whenever we go through the available holes of sizes, whatever the holes comes first, that is big enough for the process to complete its execution, we allocate that first hole to that process. So you need not have to go and search through the whole list of memories available. So whatever it is coming first, we are allocating that to the process coming, and we were completing the execution. That is called first fit. Next one is the best fit. Best fit is nothing but we'll allocate the whole which is well enough for to execute the process, which is not too large, which is not too small, so that it will accommodate, the memory will be accommodated enough for the process to complete its execution. That is called best fit. That is called best fit. And the next one is the worst fit. So worst fit is nothing but whatever the process coming for execution, what is the biggest memory we have, we are going to allocate that biggest memory whole to that process, and that leads to worst fit. Because of the worst fit, there will be the lot of wastage of memory while executing any process. So comparing to first fit, best fit and worst fit, the first fit and best fit will leads to lots of problem related to compaction. lots of problem related to memory compaction, and that can be solved with the help of the joining of the left out fragments, and then we can create a compact, and you can, this compaction can be the solution for the first and the best fit problems. So from the beginning we have seen what is memory and what are the types of memory and how we can manage the memory, what are the basics of physical address, logical address, and how we can bind this physical address and logical address, what are contiguous memory allocation, and what are the techniques we follow in the continuous memory allocations like fixed partition, variable partition, best fit, worst fit, etc., through from the contiguous memory allocation. And this is all about some of the memory management techniques available in operating system, helps you to manage a process. So thank you so much. Thank you so much for your listening. Happy learning. Thank you. We'll see again in the next series. Hello everyone.